Hi everyone, this is Shashank Gupta from IIT Bombay. I'm working as research assistant under Professor Somen Chakravarti. So this talk is all about my experiences over the past 6 months and the work that I've done over there. So in the past couple of days, a substantial number of modules on IR and semantic web have been touched upon. So I think it's about time that we look at one such practical semantic search system and the implementation level challenges involved therein. So I'll start my talk with a quick bird's eye view of the system. I'll then talk about the challenges that we faced while scaling it up, which will be followed by a detailed analysis of the consequences of a design choice. So CISO, that's what we call our semantic search system. It's an acronym for curating and searching the annotated web. So the production CISO system runs on a 14-node cluster, utilizing a web corpus of around 1.6 TB, which contains over 500 million documents. Right now, we use Yahoo as our primary knowledge base, which enables us to cover over 2 million entities and over 200,000 types. So right now, when our annotator is run over the corpus, over 61 spots for entity linking per document are identified, out of which over 21 are actually allocated to one of the entities in the Yahoo catalog. It takes around 2 days to annotate and index the entire corpus right now. So those were some quick stats about the CISO system. But how exactly do we deal with this? I mean, it's 1.6 TB and 500 million documents. How are we able to deliver results in real time? So Professor Ganesh has already talked about the work that has gone into scaling up the system. I'll borrow up some modules from his talk, which I'll be requiring for my talk. So the entire corpus is partitioned into 10 equal stripes or partitions. So these are the partitions. Each stripe is replicated to over 4 hosts for fault tolerance and parallelization. We call them buddies. This diagram shows only 2, but there are 4 of them. Each host effectively works on 1/40th portion of the full corpus. Okay. So what does this host do with its share of the corpus? It will scan a document and will pass it through standard IR cleansing modules like tokenization, stemming, and removal of stop words. It will then load up a dictionary in RAM and will match that dictionary with the token sequences in the document and will identify possible places for entity linking. We call such places as spots or lemma. Now the context of that spot, the context around that spot is wrapped around into a feature vector, which we call a context feature vector or a CFV. Please do memorize this term since I'll be using them quite often. Now a classifier is run on that feature vector and one or more, and zero or more candidate entities are selected as annotations, which are later on indexed to serve results in real time. Okay. Right now, the entire collection of lemma models is collected into a single entity. It's a highly optimized and compressed buffer. Okay. So where exactly is the Yahoo catalog over here? So Yahoo catalog is present over here. More the number of entities in the Yahoo catalog, more will be the number of spots. So basically, if you do not have Sachin Tendulkar in your catalog, then there's no point of identifying spots like Master Blaster or Little Master. Okay, so the title of my talk says web scale entity annotation. So what do I mean by that? What all modules in that workflow can be scaled up, and why would we like to do that? So the first kind of scale up that's possible is the scaling of the corpus. Let's say we move from 500 million documents to over 1 billion documents. But why? So this is a workflow again for your reference. More the number of documents in the corpus, more will the number of annotations. And hence, while serving a query, we'll have more annotations to boost up or reduce our confidence on a particular rank. More the number of documents in the corpus, more are chances of encountering a rare entity, which will enable our system to cover even the tail queries. So this is nice. This is all nice and cool, but what will the effect on the system? Obviously, since we are going to scan more documents, time to annotate the entire corpus will go up. More the number of documents, more are annotations, and hence larger will be the index. Larger the index, more index merge runs will be required, which will again translate into more time. But all this does not pose any further system level challenge, as in our current system can very well deal with the corpus scale up. So, I mean, it's very obvious that if you are going to scale up number of documents, your time will go up, but this does not pose any further system level challenge. Another type of scale up that's possible is scaling up your catalog. Let's say we move from 2 million entities in Yahoo to over 30 million entities in Freebase. What why? So the query coverage of the system depends critically on recognizing and annotating as many entities as possible. So if your query is seeking an entity which is not present in the catalog, then your system will never be able to address that query. So if your catalog does not contain Sachin Tendulkar, then you can never address queries like who's the leading run scorer in cricket. So what will the effect on the system? Migration from Yahoo to Freebase will result into over 15x growth in the entire level model set size. So that model size that we are fitting in RAM, this will scale up to over 30 GB. As Professor Ganesh talked about, right now our annotation rate is quite high. It's the reason being this level model set is small enough to be fit into RAM. But since now it's going to scale up 30 GB, it will no longer fit into RAM. Okay. Now someone might argue that why don't you buy yourself bigger RAM, or why don't you try to compress the model set size further? So my answer to that would be it's a never-ending process. As more and more data will be generated, the size of the catalog will go up. And secondly, it will be suboptimal use of RAM, since we should try to preserve as much RAM as possible for larger index runs. So the question that we face is, can this design challenge be addressed to make the system infinitely scalable? So that's what our contribution is, and is what the rest of the talk all about. Okay. So the final system that we came up with is pretty fast, but the alternative baselines that we considered was so slow that we actually had to tone down our corpus. So we sampled just 54 GB of the entire 1.6 TB, which contains over 80 million documents. We fixed our catalog to be Yahoo, and to simulate the effect of scale up to Freebase, we simulated shrinking of RAM by the same factor. And for the same reason, we ran experiments on just 20 of those 40 hosts, each using only 4 cores. This is the first baseline that we considered. In words, partition your set into minimum number of disjoint subsets such that each set can fit into RAM at once. Now make multiple passes through the corpus, each time using a different partition. But as it turns out, finding out this minimum number of disjoint subsets is an NP-hard problem. An effective heuristic for which is to sort model sizes in decreasing order, keep on packing them into a bin until it's full, upon which allocate a new bin and continue with the process. So what are the pros and cons of this approach? It's a very simple adaptation of existing system with minimal code changes, no extra network traffic since entire computation is local to the system. Those feature vectors are generated on the fly, as in they are not materialized on disk, so which saves us quite enough disk space. And the computations are statistically load balanced since the corpus has been partitioned randomly. So there's no reason as to why a particular host will take more time than the others. What are the cons? So CPU work needed to convert document into feature vectors will be repeated multiple times. So basically that loading up of models is happening over here. So the CPU work for this section will be repeated multiple times. And as it turns out, this work is not negligible as compared to the disambiguation work itself. So this segment will be repeated multiple times. How does it perform? As I said, migration to Freebase will result into 15x growth. So this diagram plots estimate of number of passes with the bin size. So the interesting number to look for over here would be the range of 100 to 200 MB, since we are simulating shrinking of RAM, and 15x shrink of our current 11 model set size will be roughly around that. So for a cache size of 100 to 200 MB, number of passes is in the range of 10 to 20. To give you an idea of what it actually means, right now a full corpus scan takes about a day. So 10 to 20 such passes will effectively mean 10 to 20 days as compared to just 2 days taken by our native system. Okay. So the immediate reaction of anyone would be to suggest, why don't you do a single pass over the corpus, and since you're not able to load up models the entire set at once, why don't you load them up on demand, as and when a spot is encountered. So we call it the caching models baseline. As it turns out, those model sizes are quite diverse and are highly skewed. So the size of the largest model being 1.37 MB and the smallest being just 13 bytes, average being 1.35 KB. And this is depicted from this figure as well. There's a huge skew towards lower sizes. The encounter rates of lemmas are highly skewed as well. So Sachin Tendulkar will be encountered quite frequently as compared to my name. So this raises hope that a cache of models with a suitable eviction policy like LRU or LFU, least recently used or least frequently used, could lead to good hit rates and faster annotation. So what are the pros and cons? Pros being the very similar: simple adaptation, no extra network traffic, safe disk space, and load balanced. Cons being, in the native system, we were loading up the entire model set at once. We were allocating a dedicated buffer for that. But now we are going to load up models on demand. So there's a possibility of RAM fragmentation. And since there's a frequent loading and unloading of models, there's a possibility that garbage collector of JVM will undergo intolerable stress. And moreover, a cache miss will almost certainly result into a disk seek, since OS buffers are anyways exhausted with a corpus runs and the indexing runs, corpus scanning and indexing runs. Scaling up the catalog might bring down cache hit rates. So let's say earlier our catalog didn't contain Sachin Tendulkar, and now it contains. So we'll be encountering spots for Sachin. So number of candidates to be cached has increased. So this indicates that cache hit rates might go down. Yep, we are estimating. Okay, the performance. So this graph tells us the miss rates, estimates of miss rates with a cache size for two popular eviction policies, LRU and LFU. LRU is somehow superior than LFU. Again, the interesting range would be 100 to 200 MB cache. So it's roughly around 10% miss rate. This might look very less, but this should be reinterpreted in the context of our application. So I'll revisit this point once more. Globally, over 0.28 million lemmas are encountered per second. And over 14K lemmas are encountered per second at each host. So 10% of that will mean around 1.4K misses per second. And ultimately, one miss leads to one disk seek. So over 1.4K disk seeks per second. And one disk seek can easily cost 10 milliseconds. So 10 milliseconds of disk seeks and 1.4K such disk seeks. So just imagine the slowdown of the system. Right. But still, there'll be a limit ultimately. And as I said, because of the intolerable stress on the JVM, garbage collector often crashed our program, saying GC overhead limit exceeded. So because of these constraints, we just present one data point with 540 MB cache, 54 GB corpus took around 7.6 hours, as compared to just 6 hours for bin cache, bin packing. So it's even worse than the bin packing approach. So how sensitive is our analysis to the catalog scale up? As I mentioned that scaling up the catalog will lead to encounter of more spots, and that should bring down our hit rates. So does it really happen? So this graph narrates the very same story. On the y-axis, you have increased number of misses per second. And on the x-axis, you have the cache size. And different lines indicate different order of scale up. So concentrate on this red line. It says 300% scale up. That means quadrupling our number of models. And this is precisely what we expect when we migrate to freebase. So this is an increased number of misses per second, right? So you can't fit a logic over here. This is the cache size, right? So yeah, this is an increase in number of misses. This is not misses per second. How many misses have increased per second? This is an increment. This is not the absolute number. Yep. Mm-hmm. Yeah, that might be the case, but I'm saying this plot is for increased number of misses per second. So, just concentrate on the previous data point. So the previous data point also indicates increase in number of misses per second. You're not getting the context over here. This y-axis says increased number of misses per second. This is not the absolute misses per second. I don't see why that should be the case. I'm not convinced with that. It should. Yeah, the absolute number does come down, yeah. So these are absolute numbers. So miss rate is coming down as you increase your cache size. That's an increment in the second graph. That's an increment in number of misses per second. So that's what I said. You just can't fit a logic in over here that what should be the curve like. Okay, this is pretty much clear, right? That this should go down. So just imagine one more line over here with a different, say with different, right. Again, why should that be the case? Okay. Let's take it offline then. Okay, so for a cache size of 200 to 400 MB, number of misses per second per host can double if the number of models is quadrupled. So as if the situation wasn't bad even now, this will make situation even worse. So your number of misses per second will almost double when you migrate to freebase. So already we were having around 1.4K misses per second. It will eventually double when you migrate to freebase. So what's an alternative baseline? So alternative baseline could be to try to convert those disk6 into network transfers. So we investigated the use of distributed in-memory key value stores like memcache and HBase. So the way these systems will work is we'll populate our lemma models into them, keyed by the lemma ID. And as and when a model will be required, as and when a lemma will be encountered, corresponding model will be pulled up from these systems. So we are expecting that this should work fine, since a lemma model is most likely to be resident in RAM at least one of the hosts. Average is around 1.37 KB. So we eventually convert those disk6 on cache miss into network transfers. So again, the pros and cons, not much stress on GC, since models are expected to be present in RAM at least one of the hosts. For the same reason, no time overhead for model unloading and loading. And ultimately, those disk6 have been converted into RAM hits at least one of the hosts and the corresponding network transfer. What are the cons? So unless replicated manually, in these systems, only one host will cater to request of all the key, cater to all the requests for a particular key, which might be quite undesirable for us since we have highly skewed distribution of lemmas. So the host that is serving the most frequent lemma can choke up the entire system, since all the requests for that frequent lemma will be redirected to that particular host. And also because of high lemma spotting rate or high lemma encounter rate, these systems might encounter quite impractical demands. I'll revisit this point. And again, as I pointed out earlier, scale up of catalog will lead to identification of more spots, and hence, if for those spots, queries will be issued to these key value stores again. So this scale up will increase that demand as well. How does it perform? Concentrate on this table. In the leftmost column, you have the lemma rank in terms of its frequency over the corpus, one being the most frequent one. The middle column says the bandwidth requirement for that to serve that particular model, and the last column says the number of queries that will be issued for that particular lemma. So just to cater to request for the most frequent lemma, a particular host should be able to serve that corresponding model at the rate of 6.65 GB per second, which is around 6,000 queries per second. It actually depends on the size of the model, right? Right. So average is 1.37 KB. Yeah, but the distribution is quite skewed. Globally, over 0.28 million queries will be issued to the key value store per second, which is around 69 GB of network transfer per second. So these are quite impractical demands. And moreover, migration to freebase will almost double the query bandwidth. As I said, identification of new spots will lead to more demands, and according to our estimates, this demand will almost double. So again, now we should be pretty much convinced that our current approach of scanning through documents and disambiguating them on the fly will not work. So what's an alternative approach? So do the work of conversion of document into CFs only once, and materialize them on disk, and scatter them over different hosts. So we call it the scattering CFS baseline. The only difference between this approach and the earlier approach is, in the previous approach, we were transmitting lemma models over the network, but over here we'll be transmitting feature vectors over the network. Okay. So, so how it will work is, just do your scanning of document and conversion into CFPs, and install disambiguators or your classifiers at different hosts, and communicate your feature vectors to those hosts. So this is determined. This is predetermined as to which all host will load up which all disambiguators, and once CFEs are generated, those will be transmitted over the network to those particular hosts, and load models on demand and those disambiguation sites, and disambiguate the CFEs. Okay, so now the question is how and when to communicate those CFEs. I mean, do you totally materialize them on disk, then only send them, or you send them on the fly? So one approach is to send the CFEs as and when they are encountered, but this is quite similar to the caching model baseline, since CFEs will be received by those disambiguation sites in totally random order. And our experiences with the caching model baseline says that, I mean, we should rather refute this approach. Another approach is to invest time upfront and actually sort the incoming CFEs. So the advantage that we get from this is that all the CFEs will be processed at those hosts in lemma order. That is, only one model needs to be loaded in RAM at once, and all the corresponding CFEs will be disambiguated in a batch. So it will lead to negligible RAM requirement, since we are loading up just one model at a time. So I mean, this looks quite favorable to us. So we went ahead and did some calculations to further convince us. So the distribution of number of CFVs is highly skewed as well. So I mean, if you want to understand number of CFVs per lemma, it's equivalent to the encounter rate of a lemma. So the minimum number of CFVs per lemma is just 1, and the maximum being 23.42 million. So again, a highly skewed distribution towards the lower side. And not only that, distribution of number of candidate entities is highly skewed as well. So minimum being just 2 and the maximum being 742. So if you want to understand number of candidate entities, so let's say for term Sachin, let's say for term John, we'll have so many disambiguations possible. But say for APJ Abdul Kalam, we'll probably have just one disambiguation. So that's what I mean by the ambiguity. So why this is all coming into picture, it will be more clear over here. So total CPU work per lemma is the product of number of CFVs for that lemma and the time to disambiguate one of them. This is plain mathematics. And the disambiguation time per lemma is a function of the ambiguity of the lemma. And we model it using a least square linear regression. It's quite a linear curve. So what it says is that disambiguating John, which has high degree of ambiguity, will take much more time than disambiguating Sir APJ Abdul Kalam. So the resulting distribution of work, which is a product of this time into the number of CFVs, is highly skewed as well. It actually follows power log distribution. Minimum work being 0.6 milliseconds and maximum being 14 hours and 12 minutes. Okay. So this tells us that we might want to replicate the models. We might to have more disambiguation sites for the frequent ones. Otherwise, we might hit a major skew problem. But we went ahead instead and we tried to omit the key partitioning or the replication, and we instead thought that why not to schedule more number of small jobs together, and why not to pack at one site, and why not to pack larger number of small jobs. So why not to pack larger number of small jobs at one side and small number of larger jobs at the other side. So that should practically balance. That should practically pack our jobs efficiently. So we did a greedy scheduling of that, which is sort task in decreasing work order and assign each successive task to the least loaded core. So job completion time went up to 14 hours and 32 minutes. The reason for that is minimum time per host was just 20 minutes and the maximum time being 14 hours, 32 minutes. So CPUs were idle for like 94% of the time. This is the computation profile. So not only the computation profile is skewed, but also the communication profile. So the blue bar indicates outbound traffic. Outbound traffic is fairly balanced since corpus is randomly striped. But look at the red bar. It says the inbound traffic, which is highly skewed. So maximum being quite natural to use MapReduce over here. So in MapReduce, you define a mapper and a reducer. Mapper will input a document and will output a key value pair. Reducer will collect all such key value pairs and will do some computations and will produce an output. If a very normal use case is indexing, you process a document with ID, you scan and tokenize it, you emit records of the form KD where for each word K in D. Reducer will collect all such KD pairs and will form a compressed posting list and will output it. So this is a normal MapReduce job. But what's the possible MapReduce expression for our approach? So mapper will input a document with IDD and will transform it to CFAs and will emit those CFAs keyed by the lemma ID. So basically, this portion of the workflow will be done by the mappers, and this portion will be done by the reducers. So reducer will input all such CFVs which are keyed on a particular lemma and will load up the corresponding model and will disambiguate them. So mapper completes up this portion and reducer completes up this portion. In the most natural map-reduce expression, we would like to use as many mappers as CPU cores and as many reducers as lemma IDs. Each reducer will load only one lemma model and will disambiguate all the CFEs keyed on that lemma. So again, we are not replicating the lemma models over here. The challenges being number of lemma IDs are roughly around 2 million. So it will lead to thousands to millions of reducers per host, and no known Hadoop implementation can handle such a scale. And again, since we are not replicating those lemma models, it will lead to larger reducer idle times because of the inherent skew present in the system. So the alternative is trust Hadoop's packing strategy and limit number of reducers. So we call it the vanilla Hadoop approach. So we choose as many reducers as CPU cores, and we rely on Hadoop's default key packing strategy, which is to hash the keys randomly into reducers. So since it's a random hash, there's a possibility that we'll achieve better packing and better CPU utilization. What's the performance? Job completion time went up to 20 hours and 90 minutes. Again, the same problem, minimum time per reducer being 16 minutes, and maximum being 17 hours, 44 minutes. CPUs are idle for like 82.12% of the time. Similar computation profile and similar communication profile. So we are still not replicating the keys. We are still not partitioning the keys. So is it still possible to obtain better backing of jobs without replication? So this is where recent work on skew mitigation comes into picture. SkewTune is one such popular skew mitigation strategy. It has been integrated into Hadoop and is available publicly. It supports dynamic and automatic reassignment of reduced tasks. That means it keeps track of nodes, and as soon as a node becomes idle, SkewTune identifies the task with the greatest expected remaining processing time, and it repartitions the unprocessed input delegated to that task amongst the idle nodes. But again, the same problem with SkewTune, it does not split keys. So similar performance, 19.5 hours, 80.7% CPU idle time. So we are now pretty much convinced that we can't get away without replicating those keys, without actually partitioning those keys. But the real question is how to decide which all keys to split up and how many such splits. Yeah, sure. Okay. So this was our approach. Okay, I'll tell you briefly what we did. So we somehow formulated this formulated this objective function. So as slides will be shared, you can go through how this was derived. So once we have this objective function, we tried to optimize it. But before optimizing it, we tried a very basic heuristic for that, and apparently it worked quite fine for us. So then after observing its performance, we went back on board and actually checked why this is performing so good, and we somehow could prove that this heuristic will incur minimum overhead and is actually in a constant factor of the optimal. So the heuristic is like this. Instead of choosing optimal number of partitions for each and every lemma, just partition top k jobs and partition them into p partitions where p is the number of reducers. So now we just need to optimize the objective to obtain this k, which is which top k jobs to partitions, So this was our heuristic, and it worked quite fine for us. Job completion time went down to just 3 hours and 47 minutes. Minimum time per reducer being 59 minutes, maximum time being 69 minutes, and percentage CPU idle time just 3%. So this is the computation profile now, and fairly balanced communication profile as well. So final annotator is 5.4x faster than standard Hadoop and 5.2x faster than even SkewTune. Okay. So we looked at the evolution of a semantic search application from a custom implementation to highly optimized MR version. Simple adaptations gave unacceptable performances. Standard Hadoop MR expression hit a serious reducer skew problem. Even recent skew mitigation techniques could not provide us modest improvements. So we then created our own performance model and optimized the resulting objective by using heuristics. And finally, we got 5.4x faster annotator than the standard Hadoop MR.
If we sorted the tasks in decreasing order of compute complexity, and you assign each task to a different user, how close would you get to this?
That's a vanilla Hadoop approach, right?
Not necessarily, right? Vanilla Hadoop will assign it randomly, but here you are sorting it in decreasing.
Okay.
So the one that takes the most time, you assign it to the first.
Mm-hmm.
The next one, you assign it to the next.
Right.
Just curious how.
So that's similar to the grading scheduling approach then, that 14 hours, 32 minutes thing. Yeah, this one.
Here you are taking the village log, assigning it to one reducer, and the next village log to the next.
Yeah. So this is just this is 14 hours, only the CPU time. We are not considering the communication time over here. So the total time will be much more than 14 hours.